Now, senior, let's continue with our electric field exercises. It says, number 6 says a charge of 2.0 times 10 power minus 5 coulomb experiences a force of 18 newtons. 2.0 charge 2.0 times 10 raised power minus 5 coulombs experiences a force of 80 newton. In this question 2, we are to find the electric field strength or intensity. That's very simple. Like I said before, electric field strength is force per unit charge acting in an electric field. So that's 80 newton divided by 2 times 10 raised. The 0.0 is not compulsory. Minus 5 coulomb. That's 80. Okay, let's simplify one after the other. 80 over 2 newton per coulomb, then 1 over 10 raised power minus 5. For in order not to confuse you, let me do it this way. Okay, times 10 raised power minus 5. Exactly. That will give us 40 over 10 raised power minus 5 newton per coulomb. Or let's leave it the way it should be. Newton per coulomb. This is the same thing as 40 times 10 raised power minus 5 newton per coulomb. And that 40 is 4 times 10. 10 is 10 raised power 1 times 10 raised power 5 minus 5 here will give us plus 5. So newton per coulomb. My answer is 4 times 10 raised power 6 newton per coulomb. That's question 6. Let's go to question 7. Question 7 says, if the force on a charge of 0.2 coulombs in an electric field is 4 newton, the electric field strength is, we are looking for electric field strength. Force is 4 newton, the charge is 0.2 coulomb. That's simple. Electric field strength is F over Q. So that is what? 4 newton over 0.2 coulomb. 4 divided by 0.2, I think, should give us 40 over 2. So that 20 newton per coulomb is the electric field strength. Number 8 says, question 8 says, the electric field intensity in a place where a charge of this experiences a this is this. Okay? Charge Q, 10 raised to power minus 10 coulomb. Force experienced, I think, 0.4 newton. Let me check that. Okay, electric field strength is what we are looking for. So electric field strength in that field where this charge experiences this force is E is equal to F over Q. Q can be small letter or capital letter. So that's 0.4 newton divided by 10 raised power minus 10 coulombs. So I'm going to be really fast now because it's not our first time. So 0.4 newton is 4.0 times 10 raised power minus 1 newton divided by 10 raised power minus 10 coulombs. So I will simplify that. It's going to give me 4.0 times 10 raised power minus 1 times 10 raised power minus 10 newton per coulomb. Is that clear? Senior. So that gives us 40. That gives us 4 times 10 raised power minus 1 plus 10. You know this is going to change to plus 10. You add it to minus 1 newton per coulomb. 4 times 10 raised power 9 newton per coulomb. That's the electric field strength in that field. Should it be number 10 or number 9? Okay, it should be number 9. Let's go. Question 9 says a point charge of magnitude 2 microcoulomb is moved through a distance of 0.2 meters against a uniform field of 25 volts. Okay, point charge Q 2 microcoulomb moves through a distance. What distance? X, or we can use S, we can use R, we can also use D through a distance of what? 0.2 meters. Okay, moves through a distance. Okay, I think I'm going to lose my question there. Excuse me. Excuse me. Okay. It's moved through a distance of what? A point charge of magnitude 2 microcoulomb is moved through a distance of 0.2 meters. Against a uniform field of intensity 25 volts per meter, the question says calculate the work done. Okay, 0.2 meters distance, electric field strength is 25 volts per meter. We want the work done on the charge. Work done on a charge is force times distance moved. You understand? We can say distance is x or r. Now, that force we have done before is EQ. That means that the work done, if you replace EQ with force, the work done will be EQ times distance. So the work done now will be the electric field strength, 25 volts per meter, times the charge. What's the charge? 2 microcoulomb. That's 2 times 10 raised to the power minus 6 coulombs times 0.2 meters. You multiply all of these, you get your work done in joules. That's how to do that kind of question. Take note. Number 10 says, if 8 times 10 raised to the power minus 2 joules of work is required to move 100, 8 times 10 raised to the power minus 2 joules of work is required to move 100 microcoulomb of charge from a point X to point Y in an electric field. The PD between X and Y is, okay, number 10, okay, work done, 8 times 10 raised to the power minus 2 joules, charge moved, 100 microcoulomb, let me be sure, charge moved is what? 100 microcoulomb, correct. What is the potential difference between them? So we are looking for V between the two fields, or between the 2 points X and Y. So let's say this is point X and this is point Y. Let's say this is point X and this is point Y. And the distance between X and Y, we don't know, but there's an electric field between them, whether going to the right, we don't know their charges, but there's an electric field between point X and Y. So it says that if a charge is moved from point X to Y, that charge is moved against the strength of the electric field. Either the electric field does work on it or it does work against the electric field. So the PD between the 2 points is V. So we always say that work done is QV. So meaning that if I know Q can be capital or small, meaning that if I know work done and V, I can know Q. So, or if I know work done and Q, I can know V. So QV is equal to W. That means V is W over Q. That will give me 8 times 10 raised to the power minus 2 joules divided by 100 microcoulomb. So that gives me 8 times 10 raised to the power minus 2 divided by 100 times 10 raised to the power minus 6 joule per coulomb. So my answer is 8 times 10 raised to the power minus 2 times 10 raised to the power minus 2. If I take this 10 raised to the power 2 up, I will have to put a minus behind the 2. Then I'll take 10 raised to the power minus 6 up too. It will be minus 6 coulombs. That gives me 8 times 10 raised to the power minus 2 plus minus 2 plus 6. This will become minus times minus plus 6, and I'll just add it to the rest. So I'll get 8 times 10 raised to the power 2 joule per coulomb. Joules per coulomb. That's the same thing as voltage, which is 8 times 10 raised to the power 2 volts. So take note of that question, very important. Next one says, find the work done in moving 2 coulombs of charge between 2 points X and Y in an electric field if the potential difference is 100 volts. Very easy, this kind of question. Work done. What's the question number? Number 10. Number 11. Work done in moving quantity of charge is 2 coulombs if the potential difference is 100 volts. Let me check that one. 2 coulombs, 100 volts. Okay. In this kind of question, the work done is QV. Work done is, given by QV. That's 2. Q is the quantity of charge, V is the voltage. That's 2 times 100. So the work done is 200 joules. Some of these questions are simple. Just get familiar with the topic and you will always earn a lot of marks from questions on it. The potential difference between 2 points A and B. The potential difference between 2 points A and B situated at a distance d apart is V. Which of the following expression gives the magnitude of the electric field? I think we have done this many times. So, number 12. Potential difference PD between points A and B is what? Is V. And the distance between them is what? D. The electric field intensity is V over D. It's as simple as that. So, sometimes electric field intensity is given in volts per meter. Voltage, PD is measured in volts, distance is measured in meters. That means the SI unit, Newton per Coulomb, is synonymous to volt per meter in electric field. So we can write the SI unit of electric field strength as N per C, or as NC raised to power -1, or as volt per meter, or volt meter raised to power -1. So that's number 12. Let's go to question 13. Says, what's the magnitude of electric field intensity between two plates 30 centimeters apart if the potential difference is 4.2 volts? Distance between the plates 30 centimeters apart. Potential difference is 4.2 volts. Assume that the plate is like a capacitor plate with negative plate and what? Positive plate. The potential between the two plates is given as what? As V. The separation between the two plates is given as D. Electric field lines of forces go from positive to negative. We always draw electric lines of forces going from the positive plate to the negative plate. So there's an electric field created between the two. The strength of that electric field is given by E is equal to V over D. That means the potential difference divided by their separation. That's what? 4.2 volts divided by 30 centimeters. Don't forget, if this 30 centimeters, we need to change it to meter, because centimeters is not the SI unit of length. So it will change to 0.3 meters. That gives us what? E is equal to 4.2 volts divided by 0.3 meters. That's 42 over 3 volts per meter, and the electric field strength is 14 volts per meter. Exactly. That's number 13. Let's go to question 14. What do we have in question 14? Says an electron of charge 1.6 times 10 raised to power -19 coulombs is accelerated between two metal plates. If the kinetic energy of the electron is this, the potential difference between the plates is, electron, the charge of an electron is 1.6 times, the charge of the electron is 1.6 times 10 raised to power -19 coulombs. We are told that the kinetic energy of the electron is 4.8 times 10 raised to power -17 joules. 4.8 times 10 raised to power -17 joules. The question says the potential difference between the plates, and so technically what we do here is very simple. Assume that these are two plates of a capacitor. You understand? Electrons will go from the negative one to the positive plate like this. Against the electric field, they must have a lot of energy before they can travel. Electric lines of forces are drawn like this. Can you see? So electrons must have enough energy that will make them move against those lines of force. So we always say that the kinetic energy of the electron will be equal to the work done on the electron by the electric field. The kinetic energy of the electron must be equal to the work done by the by the electric field in stopping the electron. So meaning that 4.8 times 10 raised to power minus 17 must be equal to QV, where Q is the charge of the electron. Where Q is the charge of the electron. So let's try and make things simpler now. So what do? We just say QV is 4.8 times 10 raised to power minus 17. Q is the charge of the electron. So I can use E for Q. I'll just say EV is equal to what? Is equal to 4.8 times 10 raised to power minus 17. That gives me what? That gives me potential difference is 4.8 times 10 raised to power minus 17 over E. And that's 4.8 times 10 raised to power minus 17 divided by 1.6 times 10 raised to power minus 19. So if you put that together correctly, you get 3. 4.8 over 1.6. 4.8 over 1.6 is 3. That's 3 times 10 raised to power minus 17 minus 19. You are dividing 10 raised to power minus 17 by 10 raised to power minus 19. Division means you subtract indices. 10 raised to power minus 17 minus 19. This division will produce this minus. So that gives you 10 raised to power minus 17 minus 19. You simplify, what do you get? That V is equal to 3 times 10 raised to power minus 17 plus 19. Minus times minus is plus. 3 times 10 raised to power 2 volts is your potential difference. Your potential difference is 3 times 10 raised to power 2 volts. So that's question 14. Take note of that question, very important. Let's go to the next one. Question 15. What's in question 15? It says a 5-volt battery. Question 15 says a 5-volt battery is connected across the plates of a 2 microfarad uncharged parallel plate capacitor. The charge on the capacitor after a long time is, okay, a 5-volt battery is connected across a 2 microfarad capacitor. Okay. This is our capacitor parallel plate. This is our parallel plate capacitor. Plus. Okay, they said it's not charged, but at the end of the day, it will look like this. Okay, 2 microfarad. The capacitance of the capacitor, that's what we should write first. The 5-volt, this is a 5-volt battery. The battery is what? 5 volt. The battery is 5 volt. So we write that voltage is what? 5 volt. The capacitance of the capacitor C is 2 microfarad. What charge will be stored on the capacitor is what we need now. So we need Q. So that means we need what? We need Q, which is the charge stored on the capacitor. Now, in capacitor calculations, we always say Q is equal to CV. So that means in this case, Q will be 2 microfarad times 5 volts. That gives you what? 10 microcoulomb. So the charge stored on the capacitor will be 10 microcoulomb. You understand? 10 plus 10 on the parallel plate and minus 10 on the plus 10 on the positive plate, minus 10 on the, so same charge is stored here, minus Q here plus Q here. So take note of that too. Number 16. Question 16 says question 16 says a parallel plate capacitor has a common plate area of 5 times 10 raised to power minus 8 meters squared and plate separation of 2 times 10 raised to power minus 3. Assuming free space, what is the capacitance? Okay, we first need to draw our diagram. This is what a parallel plate capacitor looks like. You understand? Minus, plus, plus. So this is a parallel plate capacitor. We need to get the separation D. What is separation? Let's go ahead and get the separation. We are told that D is what? That the separation between the plates is 5 times 10 raised to power minus, no, that's the area. 2 times 10 raised to power minus 3. We are told that the separation is 2 times 10 raised to power minus 3 meters, and that the area of the plate is 5 times 10 raised to power minus 8 meters squared. I hope I got that right. Okay, assuming free space is between it. Assuming there's free space between the plates, what is the capacitance of the capacitor? EO is 9.0 times 10 raised to power minus 12. Okay, we are told that the permittivity of free space is 9.0 times 10 raised to power minus 12. 9.0 times 10 raised to power minus 12. Check the SI unit. C squared n minus 1 m minus 2. C squared n minus 1 m minus 2. So we are to find the capacitance of the capacitor. Now the capacitance of the capacitor is equal to EO is equal to EA over D. But in this case, the material between the plates is it's free space. So that will give us what? That will take us to the next line where we do substitution of values. What do we get when we substitute values? We will get 9.0 times 10 raised to power what? Minus 12. 9.0 times 10 raised to power minus 12 times 5 times 10 raised to power minus 8. Everything is in SI unit, so I can just substitute straight. Over D, separation. What is separation between the plates? 2 times 10 raised to power minus 3. 2 times 10 raised to power minus 3. What will this give us? 9 times 5 over 2. Let's put the powers together. 10 raised to power minus 12 times 10 raised to power minus 8 over 10 raised to power minus 3. This 10 raised to power minus 3 here, I can take it upstairs. I can take 10 raised to power minus 3 upstairs and change it to 10 raised to power minus 3. Minus 3 will become 10 raised to power what? Plus 3. I don't want to write too many steps, so you just try and learn it like that to make our work faster. So this is 45 over 2 times 10 raised to power minus 12 minus 8 is minus 12 added to minus 8 is minus 20. Minus 20 plus 3. 45 over 2 is 22.5. So this is 22.5 times 10 raised to power minus 17. So the capacitance of the capacitor will be 2.25 times 10 raised to power 1 times 10 raised to power minus 17. Add 1 to minus 17. 1 plus minus 17 will give you 1 minus 17. So the capacitance of the capacitor is 2.25 times 10 raised to power minus 16 farad. So that's how we calculate capacitance, knowing the space, the material between the plates of a capacitor, knowing the area, knowing the separation between them. So number 17 says 250 microcoulomb parallel plate capacitors. 250 microcoulomb parallel plate capacitors are connected in series. The combined capacitance is then connected across a 100-volt battery. The charge on each plate of the capacitor are okay. What number should that be? Okay, number 17. I think we are moving forward. 250 microcoulomb. Parallel plate capacitors are connected in series. Oh, I've made a mistake there. This is parallel. They are connected in series, so they should be like this. And the combination is connected across a 100-volt battery. 50 microcoulomb, 50 microcoulomb, 100-volt battery. the question says we should the question says the charge on each plate of the capacitor is, how do we get the charge on each plate of the capacitor? That's easy. First thing, let's find the total charge of these two put together and call it, Q total or QC. Now, the total charge on the two, what will it be? The total charge on the two, Q total, is equal to what? The total charge on the two is equal to 150 plus 50. Let's put it that way. 50 microcoulomb plus 50 microcoulomb. That gives us what? That gives us 100 microcoulomb. Let's now assume that we have just a single, 100 microcoulomb capacitor on a 100 volt battery. Let's just assume we have just a single 100 microcoulomb capacitor, 100 microcoulomb on a 100 volt battery. So what will be the charge? What will be the capacitance of this capacitor? Or is that not what? The charge on each plate of the capacitor. I think there's a mistake here. That's what was confusing me. This is not meant to be, coulomb. It's meant to be microfarad. So those are the capacitance of the capacitor. We are not looking for their charges. So let's remove all this. Sorry if you've written that and I've made you cancel in your note. So let's take that again. Now, first thing we need to do here is to find C total. To find C total, we use reciprocals. Let's do it this way. 1 over C total is 1 over C1 plus 1 over C2. So that means 1 over C total is 1 over 50 plus 1 over 50. What does that give us? LCM is what? 50. 50 and 51 times 1, 1. 50 and 51 times 1, 1. So 1 over C total is what? 2 over 50. So 1 over C total is 2 over 50. If you cross multiply, you will get 2C total is 50. C total is 50 over 2. And the total capacitance of the two capacitors is 25 microfarad. So let's now assume that you just have a 25 microfarad capacitor connected to 100 volt. 25 microfarad capacitor connected to 100 volt battery. How will you get the charge on this capacitor? That's what we now need in our question. You understand? How will you get the plus or minus charge? How will you get the charge on the capacitor? Now, using Q is CV. This is our C. This is our C, total capacitance, and this is our what? Our V. So using Q is equal to CV. Using Q is equal to CV. Using Q is equal to CV. Total charge in this question will be total capacitance of the two capacitors times the voltage across their combination. That will be what? 25 microfarad times 100 volts. So that's what? 2500 microcoulomb. So my answer is 2.5 times 10 raised to power 3 times 10 raised to power minus 6 coulomb. 3 minus 6. Add 3 plus 3 to minus 6. You get what? Minus 3. So the total charge on the two capacitors put together. The total charge on the two capacitors put together is 2.5 times 10 raised to power minus 3 coulombs. Now, 2.5 times 10 raised to power minus 3 coulombs. What does that mean? 2.5 times 10 raised to power minus 3 coulombs. That means each capacitor, that means each capacitor will store that total charge. This one will store what? This one will store That means each capacitor, let's put it that way, each capacitor will store a charge of 2.5 times 10 to the power minus 3 coulombs on its plate. Let's continue. Number 18, plus Q minus Q 236. In the figure below, if the EMF of the battery is 12 volts, the potential difference across the 6 microfarad capacitor is what? Okay, number 18, 236, 12. So I don't forget. 1, 3, 236, 12. Okay, this is 2 microfarad, this is 3 microfarad, this is 6 microfarad, and the EMF of this source is 12 volts. Is that clear? Now we want the PD across this. We want the potential difference across this. Note that the potential difference across each one, if added, let's say V2, V3, V6, if you add everything, it should give you 12 volts. Their charges are the same. The charges they store is the same, but they don't have the same PD across them. So what we should do here is very simple. Let's get the Q. Let's get the total charge stored by each one. So 1 over Q total, 1 over C total. We should find, to find the total charge stored, we should first find, to find the total charge stored, we should first find the total combined capacitance of all the 3 capacitors. Are you getting what I'm saying, senior? So we should first of all find the combined capacitance of all 3 capacitors. So what we will now do after getting our effective capacitance or the total capacitance, we know that we will now assume that all of these 3 are just one capacitor and that the same charge will be stored across their plates. So, it is the same charge plus Q stored here minus Q here. That will also be transferred here minus Q. That will also be transferred here plus Q minus what? Q. So you take it like that, plus Q minus Q plus Q minus Q till you get to the end. So let's go. First of all, we should find total capacitance of all the 3 capacitors. Is 1 over C total is equal to 1 over C1 plus 1 over C2 plus what? 1 over C3. So 1 over C total is 1 over 2 plus 1 over 3 plus what? 1 over 6. The LCM of all 3 is 6. That's 3 plus 2 plus 1. That gives you what? 1 over C total is 6 over 6. So if you do it correctly, C total will be equal to what? 1. Because this means 1 over C total. This means 1 over C total is 1 over 1. So when I cross multiply, C total is 1 microfarad. So the total charge stored will be, we always use Q is equal to CV. So that means total charge stored, on the, on all the capacitors put together as one, total charge stored in the, in the total capacitance is equal to C total times V. That gives me what? 1 microfarad times 12 volts. 1 microfarad times 12 volts. So the total charge stored is equal to 12 microcoulomb. That means that it is 12 microcoulomb that will be stored on the left here, minus 12 microcoulomb on the right here, plus 12 microcoulomb here, minus 12 microcoulomb here. Also, plus 12 minus 12 plus 12 minus 12. It is the same quantity of charge that gets transferred from one plate to another throughout. So what does it mean? To now get the voltage, across the 6 microfarad capacitor, that's very simple. Just assume that this is your capacitor. Just assume that this is your 6 microfarad capacitor and you want the voltage across it. You want the voltage across it. You know the charge it is storing. you know that it stores 12 microcoulomb charge, like we found here. You know it also stores a charge of 12 microcoulomb. So I know Q, I know C, 6 microfarad. That's the capacitance of the 6 microfarad capacitor. Then I know the voltage. I'm looking for the voltage across it. Using Q is equal to CV. That means 12 microcoulomb is equal to 6 microfarad times V. You understand? Q is equal to CV. This is my C, capacitance, which is 6 microfarad. And this is my what? My voltage that I don't have. So that means micro will cross micro. Look at this very well. Micro will cross micro. These letters don't mean anymore. So I just have 12 is equal to what? 6V. 6V is equal to 12. V is equal to 12 over 6. So the potential difference across the 6 microfarad capacitor is 2 volts. Take note of this question. It's very important. Number 19. Okay, I think that was 18. Number 19. C1, C2, C3. What's the total capacitance in the represented by the diagram? Okay, what is the total capacitance in the diagram above? That's what they mean. What's the total capacitance in the diagram above? When capacitors are connected in parallel, we just add normally to get their total capacitance. So in this combination, in this combination, C1, C2, C3. I hope I'm right. Okay, C1, C2, C3. In this combination, C1, C2, C3. Okay. There should be a source of EMF here. V. In this combination, C1, C2, C3, the total capacitance of all three capacitors, the total capacitance of all the three capacitors, C total, is equal to C1 plus C2 plus C3. It's as simple as that. Just add arithmetically and you get the total capacitance. Number 20. Question 20 says, two capacitors of capacitance 0.4 microfarad and 0.5 microfarad are connected in parallel and charged to a potential difference of 50 volts. Determine the total charge acquired. Okay. Connected in parallel. $50 volts here. .5 microfarad, 0.4 microfarad, 0.4 microfarad, 0.5 microfarad are connected in parallel. They are connected in parallel, and they are connected in parallel and charged to a 50 volt PD source. Determine the total charge acquired. Okay. Total charge acquired is total voltage times total capacitance. So what we need to do first to get Q total, what we need is Q total. But using Q is equal to CV, we will do Q is equal to C total times V. But before we can get total Q, we have to get C total first. C total will be 0.4 microfarad plus 0.5 microfarad. Can you see that? So total capacitance will be 0.9 microfarad. So if we want to get the total charge, it will be 50 times 0.9 microfarad, 50 volt times 0.9 microfarad, and that will be what? 45 microcoulomb. The total charge stored by the two capacitors is 45. The total charge stored by the two capacitors is 45 microcoulomb. Let me give you a few questions as your classwork to practice. Let me give you a few questions to practice as your classwork. Okay, or in order not to waste our time, I'll just write the questions and send you the snapshots. That's all for now. We will continue from there in the next video.